Okay, let's dive right into the DKD R 5-7 guidelines and uncover how we truly measure the extreme microclimates inside climatic testing chambers. If you work in engineering, quality assurance, or product testing, you know perfectly well that climatic chambers are the ultimate proving grounds for our products. But honestly, how do we know the chamber is actually doing what it says it's doing? Well, today in this explainer, we're cracking open the official calibration guidelines to see exactly how the pros validate these incredibly complex machines. Here is our roadmap for today. We're going to hit the climatic chamber challenge, define the useful volume, look at the 3 calibration methods, hunt down the 4 invisible uncertainties, and wrap up with the final calibration result.
All right, Section 1, the climatic chamber challenge.
When you place a critical, expensive component inside a testing chamber, precision is literally everything. But I want to hook you immediately with this question right off the bat, because we really need to debunk the myth that a climatic chamber is just a perfectly uniform box of hot or cold air. The display panel on the front might confidently declare that it's exactly 85 degrees Celsius and 85% relative humidity inside. But is that actually the temperature of your product? No way. The reality is that a climatic chamber is a churning, dynamic weather system. You've got varying air velocities, thermal radiation bouncing off the walls, drafts, and subtle hot and cold spots. That display, it's really just one single sensor's opinion. The DKD R 5-7 guidelines exist specifically to map out and quantify the chaotic reality happening behind that closed door. Moving on to Section 2, defining the useful volume. Now, if you take away just one thing today, please let it be this concept. You aren't actually calibrating the entire chamber. You're only calibrating this highly specific space known as the useful volume. This is the exact 3-dimensional space spanned by the measuring locations of the sensors you use during the calibration process. So why does this matter? Because according to the guidelines, the physical corners and the extreme edges of the chamber's interior, basically any area outside of where your sensors are placed, are uncalibrated territory. The DKD R 5-7 makes it crystal clear that the calibration is only valid for this spanned, useful volume. If you place a sensitive test specimen outside this invisible boundary during a real-world test, you absolutely cannot guarantee the environmental conditions acting upon it. Which brings us to Section 3, choosing your calibration method. The guidelines actually give us a highly tailored approach depending on what we need to prove, offering 3 distinct flavors. We've got Method A, Method B, and Method C. Method A focuses on the unloaded useful volume, meaning the chamber is completely empty. This establishes the pure baseline performance of the machine. Then we have Method B, which evaluates the loaded useful volume, and finally Method C, which doesn't actually span a volume at all. It only calibrates specific isolated measuring locations. You'd really only use Method C if you have a highly specialized setup where you only care about the exact pinpoint spots where a product will sit, rather than an entire 3-dimensional space. Now, Method B is a real game changer because it's uniquely rigorous. It forces us to see how the physical presence of your test products alters the chamber's internal climate. To even qualify for Method B, you have to fill at least 40% of that useful volume with test bodies, or a typical load that matches your daily operations. This validates the chamber in its actual working state. But here's the brilliant part of the guideline. If you choose Method B, you're still required to take an additional measurement at a central reference location while the chamber is empty. By comparing the empty state to the loaded state, metrologists can isolate and calculate what's called the loading effect. It's basically a mathematically precise way to say, here is exactly how much your product is messing with the chamber's airflow and temperature distribution. Let's dive into Section 4, the 4 invisible uncertainties. We're talking about the 4 invisible gremlins constantly acting upon the sensors and products in your chamber. First, spatial inhomogeneity. This refers to the differences in temperature or humidity from one physical spot to another. Second, temporal instability, which is how much the climate fluctuates over time in one single spot. Third is the radiation effect, where heat transfers invisibly from the chamber walls. And finally, the loading effect, which, as we just saw, is the thermal disruption caused by the sheer physical mass of your test items. Let's look at how the guidelines actually calculate these. To lock down spatial inhomogeneity mathematically, the DKD R 5-7 doesn't just ask you to guess. You have to calculate the absolute maximum deviation. You do this by finding the greatest difference between your central reference sensor and any of the measuring locations out at the corners of your useful volume.
You're essentially drawing a mathematical boundary box. You're saying, okay, under these specific conditions, the temperature at the absolute worst possible spot in this volume deviates from the center by no more than this exact amount. Then, building on that, we take that maximum deviation we just found and convert it into a standard uncertainty metric. The guidelines require us to use a rectangular distribution, which means dividing by the square root of 3. In plain everyday metrology terms, this means we assume the true temperature or humidity has an equal probability of being literally anywhere within those maximum deviation bounds we just set. It's a beautifully conservative approach, and it ensures our final error margins are absolutely rock solid. Now, in calculating our next gremlin, temporal instability, you just have to remember this golden rule of 30. The guidelines state you can't just flip the chamber on and start measuring. No, you must wait at least 30 minutes after steady-state conditions are reached, meaning the temperature isn't systematically drifting up or down anymore. Once that initial 30-minute stabilization period is done, you must then record at least 30 measurement values over the next 30 minutes. This rigorous rule of 30 ensures that any short-term cycling from the chamber's heating or cooling compressors is fully captured and averaged out in your data. Next up is the radiation effect. This happens because the inner walls of the chamber often sit at a different temperature than the circulating air, and they beam heat right into the products. To capture this tricky effect, we do something incredibly clever. We compare readings from two totally different materials right in the center of the chamber. On one side, we use a thermometer with a high emissivity surface, like Teflon, which absorbs thermal radiation super easily. On the other side, we use a thermometer with a low emissivity surface, like polished nickel, which reflects that radiation away. By comparing the subtle temperature differences between these two specific probes, we can mathematically extrapolate what the true air temperature is, completely independent of the hot or cold walls surrounding it. And finally, Section 5, the final calibration result. When you actually receive a formal DKD R 5.7 certificate, you won't just see a single temperature telling you your chamber is good to go. You will see distinct, meticulously documented values. You get the controller adjustment, which is the basic difference between what your chamber's display says and what the reference standard actually says, right alongside the calculated spatial inhomogeneity. This tells you exactly how much variance you're dealing with across your entire useful volume. Likewise, if you went with method B and loaded your chamber, the precise impacts of the radiation effect and the loading effect are laid out bare on the certificate. This level of granular detail proves that your specific microclimate is fully understood. You aren't guessing anymore. You know exactly how the chamber behaves empty, how it behaves full, and exactly how much uncertainty exists in the air directly around your product. So I'll leave you with this provocative thought to ensure you never look at your climative chamber as just a simple hot box, ever again. Knowing what we know now about the DKD R 5.7 guidelines, these strict spatial boundaries, and those invisible thermal effects, how confident are you in the physical placement of your product during your next critical test? Remember, precision isn't just about turning a dial on a display, it's about truly mastering the space. Thank you so much for joining me on this explainer. Keep questioning, keep measuring, and I'll catch you next time.